Last lecture, we introduced the Cartesian plane coordinate system. This lecture, we will discuss how to visually represent an algebraic equation on this plane. Let's begin by considering the equation y equals 2x plus 1. Note that there are two variables here, x and y. Since x and y are variables, they have no definite value. Rather, they represent some number in general. And there are various values of x and y that can satisfy this equation. Not all x's and y's will work. For example, x equals 0 and y equals 0 won't work, because if we substitute 0 for the y and 0 for the x, we would get 0 equals 1 when we plug it in, and that obviously is false. However, x equals 1 and y equals 3 would be an allowable choice for such variables, because when we substitute into the equation y equals 2x plus 1, and we put a 1 instead of the x and a 3 instead of a y, we get y, which is 3, equals 2 times 1 plus 1, which is also 3, and that's true. X being 0 and y being 1 is another such allowable choice, as plugging that in, we get 1 equals 1. What we can do is to plot these possibilities of the variables x and y in the Cartesian plane and see what picture we get. Note that we can let x take on any value we want, and the y value is determined by the equation y equals 2x plus 1. So if we want to pick x equals negative 1, then the value of y is forced upon us, where y equals 2x plus 1, which means y equals 2 times negative 1 plus 1, or negative 2 plus 1, which is negative 1. So y has to be negative 1, which means that x equaling negative 1 and y equaling negative 1 is another choice of the variables that satisfies the equation y equals 2x plus 1. Let's make a little table starting with x minus 2 and x equals minus 2 and going until x equals 2. So that the value of x forces the value of y. Where x is negative 2, y has to be negative 3, because 2 times negative 2 is negative 4 plus 1, which is negative 3. As we just discussed, where x is negative 1, y is also negative 1. Where x is 0, so y is 2 times 0 plus 1, which is positive 1. Where x is 1, y would be 3, because it would be 2 times 1 plus 1, which is 3. Where y is 2, then where x is 2, then y would be 2 times 2 plus 1, which is 5. So we have a list of points that match both criteria. The points are negative 2, negative 3, negative 1, negative 1, 0, 1, 1, 3, and 2, 5. Let's plot these points out on the Cartesian plane. There are, of course, many other possible points. We can let x be negative 3 and then y is negative 5, and so forth. There will be infinitely many such points. In fact, x doesn't have to be an integer. We can let x be a half, which makes y 2. The points that we put in the chart are just some of the points. However, even if we plotted as many as we wanted, we get the same idea of what's going on. It seems as though all these points fall on a straight line. In fact, if we connect all of these points on this graph, we do get a straight line. So the graph of y equals 2x plus 1 is a straight line. Let's try to understand that the numbers 2 in front of the x and 1 by itself represent this line. The 2, in this case, the number next to the x, is the slope of the line. Take any 2 points on this line, let's say 0, 1, and 1, 3, and compute their slope. The slope is the second y minus the first y divided by the second x minus the first x, or in this case, 3 minus 1 divided by 1 minus 0, which is 2 divided by 1, which of course is 2. So the slope of this line is 2. Where you have y by itself on one side, whatever coefficient is next to the x is the slope of the line. What about the number 1 at the end of the equation, y equals 2x plus 1? What does that number tell us? The answer is that that number is the y-intercept. The y-intercept is where the graph crosses the y-axis. Note that the y-intercept is where the x has a value of 0. So when we substitute 0 into the equation y equals 2x plus 1, we get y equals 2 times 0 plus 1, which is 1. Y equals 1 in this case. Therefore, the y-coordinate of the y-intercept is 1. In general, Cartesian plane lines are established by an equation that looks like y equals mx plus b, where m and b are some numbers. And that will be a graph where the slope is the m and the y-intercept is the b. The algebraic expression on the right side of the equation, or mx plus b, is a linear polynomial, since its highest power of x is 1. This justifies the terminology for the same, since we're talking about linear equations. Linear polynomials are called linear because when they're graphed, their graphs are lines, hence the name linear. Let's do one more example. Consider the equation y equals negative x minus 3. Here the slope is m equals negative 1, because the coefficient of x is negative 1. Even though there is no coefficient, we could put a 1 in front of it, and we have a negative there. So m is negative 1, and the y-intercept has a y value of negative 3. This will be the graph of the line. As before, we can plot a few points. We can make a small table showing some of the values. When we designate x values, we can then determine y values. Where x is negative 2, y is negative 1. Because negative 2 is 2, minus 3 is negative 1. Where x is negative 1, y turns out to be negative 2. Where x is 0, y is negative 3. Where x is 1, it would be negative 1 minus 3, so y would be negative 4. Where x is 2, it would be negative 2 minus 3, which would be negative 5. Be careful about making sure to apply any double negatives that apply in these formulas. Here are the points plotted and then connected in a line. The slope of this line will turn out to be negative 1, as we discussed. We can check this by picking any 2 points on the line, let's say the 1, negative 4 and 2, negative 5. Then the slope is negative 5 minus negative 4 divided by 2 minus 1, which is negative 5 plus 4 divided by 1, which is negative 1 divided by 1, which of course is negative 1. The y-coordinate where the line crosses the y-axis is negative 3, which is what we observed earlier the y-intercept had to be. Whenever we are asked to graph a line y equals mx plus b, we don't need to plot this many points. We only plotted 5 points in these examples for illustrative purposes. Now that we know that linear polynomials graph as lines, we can take advantage of this. All we need to do is plot 2 points, since 2 distinct points determine a straight line. For example, if we had to graph y equals 7x minus 11, we can just let x equal 0, and then y has to be negative 11. And we can say when x is 1, y would have to be negative 4, because it would be 7 times 1 minus 11. Therefore, we get 2 points on the line, 0, negative 11, and 1, negative 4. Plot these points on the graph and then connect them with a straight line. This will be the equation, or this will be the line that represents the equation y equals 7x minus 11. Let's look at another example. Given the line y equals 3x plus 9, find the x-intercept, a concept we haven't discussed yet. The x-intercept is where the line crosses over the x-axis. Where the line hits the x-axis is the point where the y-coordinate is 0. So to solve this, we can set y equal to 0 and get the equation 0 equals 3x plus 9. Now all we need to do is solve this equation for x. The solution to the equation, if you subtract 9 from each side, you end up with 3x equals negative 9. Divide each side by 3, and you have the answer as x equals negative 3. So the x-intercept in this case is negative 3. What about if you have 2 points and you want to deduce the equation from them? Let's look at an example. Let's say we have a line with the points 1, 3, and 2, 9. Since we're given 2 points, we can draw a straight line through them, and we are asked to find an equation for this line. We know the equation of a line is in the form of y equals mx plus b. We need to find what the m is equal to and what the b is equal to, the m being the slope and the b being the y-intercept. Let's start with the m first. Since the m is the slope of the line, we can compute the slope between these 2 points of the second y minus the first y divided by the second x minus the first x, or in this case, m equals 9 minus 3 divided by 2 minus 1, which equals 6 divided by 1, which is 6. This means our equation so far is y equals 6x plus b, because it remains to be seen what b is equal to. One way to do it is to simply plot these points on a graph and extend the line and look visually to where it crosses over the y-axis, and wherever it crosses over the y-axis is the y-intercept, since b, after all, is the y-intercept. But this is not necessary. We can be even more clever. We know that 1, 3 is a point on this line, so when x equals 1, we know that y equals 3. Substitute those numbers into the equation, y equals 6x plus b, and we get 3 equals 6 times 1 plus b, so that 3 equals 6 plus b. Solving for b, subtracting 6 from each side, we get b equals negative 3. Therefore, the equation of this line is y equals 6x minus 3. You may wonder what would happen if we used 2, 9 instead and substituted those values into the equation, and the result will be exactly the same. b will still come out to be negative 3. In this case, y would be 9, 6x would be 6 times 2, which is 12, and you'd have 9 equals 12 plus b, and solving for b, you get b equals negative 3. Next lecture, we'll study graphs of quadratic equations, those being degree 2 polynomials. In this case, we won't get lines, but curves, called parabolas.